Morning, everybody, and a very warm welcome to this exceptional morning where we've got the Oxford Discrete Maths and Probability seminar from the morning rather than the afternoon. It's a very great pleasure to welcome David Croydon, who's speaking to us from his office in Kyoto. As usual, if you have questions, please ask them in the chat. Everybody is muted by default, and Alex and I will decide whether to take the questions kind of immediately if they are some sort of clarification question, or to take them at the end if there's something a little bit more open-ended. David's going to be speaking on the scaling limits of the 2- and 3-dimensional uniform spanning trees. David, over to you.
Okay, so, well, thanks, Christina and Alex, for the invitation, of course, and well, everyone else for waking up to come to the seminar. So yeah, I'll be talking about uniform spanning trees, and so I think last week actually you had another talk by Asaf Nakmias on the same model. So maybe those at least that came to the seminar last week already know something about this. But if not, then I'd say don't worry. I'm going to start from the beginning, and probably the first half of the talk will be a little bit slow if you kind of do know something about the uniform spanning tree. But hopefully that puts everyone on a sort of similar page to begin with. Yeah, I should also say I realize this is the discrete maths seminar, and in some sense, although the uniform spanning tree is kind of course, a classical result in kind of discrete, a classical model in discrete mathematics, actually kind of my main focus is really on the sort of continuous fractal objects that arise as its scaling limit. So maybe I might drift a little bit outside the kind of area of the seminar, but hopefully by not too much anyway. So that's the sort of general topic. And yeah, finally, I guess before I start, I should put all the acknowledgements here at the top. So all of the work that I talk about is joint, comes from 2 joint projects. And so both of them involve people from University of British Columbia and also Kyoto. And so in the 2D case, the work was done jointly with Martin Barlow and Takashi Kumagai. And in the 3D case, everything I talk about was joint with Omer Angel, Sarai Hernandez Torres, and Daisuke Shiraishi. So these also contributed to the project. Okay, so anyway, to start with, let's introduce the model. And so although the title was Uniform Spanning Trees, a kind of slightly more general model is that of the uniform spanning forest. And well, this is a model that has kind of a rich history on many kinds of graphs, but to sort of keep the focus close to what I'm going to talk about, let's just kind of introduce the model on ZD. And yeah, I think, like I say, you met the uniform spanning tree on a finite graph last week. So let's kind of start off by thinking about a finite graph where it's kind of easy to define a uniform spanning tree. So let's just take, say, a box in ZD. We'll kind of use n to represent sort of the scale factor here. And so for any finite connected graph, we can define a spanning tree. So namely just to be a subgraph of the original graph that connects all the vertices and has no cycles. And so, yeah, actually this picture is maybe not the best because I actually put on wide boundary conditions. So that means that I thought of the boundary as one vertex rather than a whole load of separate vertices. In this story, it's not going to really matter, but I guess for some graphs it might do. But anyway, this is a finite graph. We can define a finite collection, or there's a finite collection of these kind of spanning trees. And so we can choose one uniformly at random. And that's the uniform spanning tree on this graph. And so, like I said, that's kind of an easy thing to understand in the finite setting. And well, kind of a natural thing to want to do is we've got this parameter n here. We want to let n go to infinity and see what happens. So can we define, sort of extend this model to the whole of ZD? And so P. Mantle showed indeed that we can. So in the sense that as we let n go to infinity, then there exists a local limit of these graphs. And so if you're not familiar with this terminology, so I think, again, maybe Asaf used this last week if you were here, but if not, then what this means is that if we look in any kind of finite box, so let's just say take a box of, I don't know, size 10, and look at the uniform spanning tree in there, or the part of the uniform spanning tree in there, and let n go to infinity, then what we see in this box of size 10 or so, then this converges to something in the limit, and so this would be the part of the limiting space inside that box. And of course, it's kind of easy to understand that what you see inside this box, it's sort of got consistent distribution over different sizes of box, and so we can use this to define a subgraph of the whole lattice. And so this is the curly U here, and we call this the uniform spanning forest on ZD. And so, yeah, a couple of subtleties here. So, yeah, I mentioned about the boundary conditions. So it doesn't matter in this particular graph what ones we use. So whether we kind of wire the boundary, have this as a single vertex, or view them as free boundaries, so all the boundary vertices as really separate ones, we end up with the same limit. So it's kind of robust in this sense. It's also robust in the sense that if we use a different exhaustion of ZD, so if we kind of take a different sequence of growing domains, then we'll also end up with the same limit. So it's kind of a reasonably well-defined object. What's easy to see is that the graph that we get won't have any cycles, because if we don't have any kind of cycles in any of the finite graphs, we're not going to make one in the limit. What's not obvious a priori and not true is that actually, although each of these finite graphs is a graph tree, so namely a connected graph, it's not actually true that the limiting object has to be connected. And so you can kind of understand that if you think in this picture here, I can have different clusters coming in from the boundary, and they might or might not meet sort of close to the center of the box. And so as we let n go to infinity, it's kind of a non-trivial question to ask whether the graph we end up seeing is a connected one or not. And P. Mantle answered this in his paper in, I think, the 90s, where he constructed the uniform spanning forest, and he showed that the answer to this depends on the dimension. So if we're in dimension 5 or higher, then we actually see a disconnected graph. So we can have sort of different infinite components of the graph, and so we call this a uniform spanning forest, each of the connected components, of course, being a tree. And so we have a collection of these making a forest. In low dimensions, the graphs that we see, so in 2, 3, and 4 dimensions, actually we do see a tree. So we see a single connected component. So we can really think of this as a spanning tree of the integer lattice in these dimensions. And yeah, as might become a little bit clearer later in the talk, this has something to do with the way in which random walks intersect depending on the dimension in space. And so, yeah, I won't say too much about why this is the dimension of interest here, but maybe those of you that know a little bit about random walks will kind of would already be able to guess why this was true, even if you didn't know already. So yeah, so this is the model that I'm going to be interested in, this curly U in dimensions 2 and 3. Before I kind of talk about this, I guess for a discrete maths audience, it's probably already a natural enough model if you didn't meet it before that you can understand that this is kind of an interesting thing to study. If you didn't, or if you're not kind of motivated by that, then there's kind of a range of other kind of words that I put here that, yeah, I kind of thought of after I wrote the slides, hence they appear just in a text file here. But yeah, so there's kind of many connections to other kind of interesting areas of maths and probability that kind of further motivate the study. So I think last week, for example, in the SAS talk, if you were here for that, then you would have seen sort of strong connections between the law of the uniform spanning tree and kind of electrical potential theory. So kind of famously Kirchhoff in the 1850s, well, proved, I guess, what people might know as the matrix tree theorem, which has as an easy application this statement that if you ask what's the probability that the uniform spanning tree uses a particular edge in the graph, so maybe let's say between, say, the origin and a neighboring vertex here, actually this turns out to be just equal to the effective resistance in the underlying graph of that edge, between those two neighboring vertices, I should say so. And so this is kind of one way to see this connection, but of course there's many others as well, and applications of this result. Apart from that, it's got kind of motivation from statistical mechanics. So it's kind of easy to understand how it arises as a limit of a random cluster model, at least intuitively. So again, if you don't know this model, so this is kind of like percolation, but we weight the number of clusters, to be either small or large, depending on a parameter in the model. And so somehow the uniform spanning tree appears as a limit as we kind of condition percolation to have a small parameter, so a small chance of including edges, but also choose the parameter controlling the number of clusters to weight more highly configurations with a small number of clusters. And so you can kind of understand if you want a small number of edges, but also a small number of clusters in the graph, if you kind of take the right limit, then you're going to end up with a tree, because of course this is just a single cluster and the smallest number of edges that you can achieve that is through a tree. And so that's how we can see that. And so that particular result was proved by Hegström, I believe also about 25 years ago or so. Yeah, another model that I will definitely talk more about today, and that's very strongly related to the uniform spanning tree, is that of the loop arrayed random walk. And so I won't say too much about this now, but of course this is the kind of connection here goes back again to the work of P-Mantle, where he was proving these kind of properties of these basic properties of the uniform spanning tree. And it's also kind of gives an important has an important role in the kind of recent history of conformally invariant scaling limits, kind of pioneered by Oded Schramm and his co-authors. And in particular, in the paper in which he introduced the Schramm-Loevner evolution, it was the loop arrays random walk that was the kind of first model that he really understood that this was what the scaling limit, that this SLE type scaling limit should be. And of course, since then, there's been much work on all sorts of other models in two-dimensional statistical mechanics where these kind of SLE type curves appear. And so again, I think I don't really want to give a review of this area, but this is just for people that haven't met it before. There's a whole kind of rich connection to other models through this theory. Yeah, more recently there's been some nice work by Tom Hutchcroft. So I saw he may be talking in this seminar later in your series. So he kind of has shown a nice connection in high dimensions between a model called random interlacements, which was introduced by Snitman, and the uniform spanning forests in high dimensions. And in particular, he's been able to use this to study various properties of uniform spanning trees. And so this is a nice new development in the area. And so there's many other kind of interesting stories here that I won't have time to talk about, but of course it's yeah, a very interesting model, I would say. It's the kind of basic point. Yeah, so that's the sort of brief background. As for my motivation, I'm kind of, like I say, going to be interested in scaling limits. So let's start to think a little bit about that. And so in particular, this is in a sense a bit of a perpendicular question to the kind of question of local limits. So I think, like I say, last week you had Asaf Nias talking about local limits of a kind of uniform spanning tree type model. And in some sense, the local limit kind of framework is answering questions about what happens kind of, well, obviously locally. So it's kind of telling you about the finite structures that you see within the graph. And I'm going to be looking at scaling limits. So namely, what are the kind of large scale properties, the asymptotic kind of structural properties of the graph in question. And one thing that's kind of course, not very clear on these kind of pictures where we draw things in ZD. So this is a 2D case, this is a 3D case. It's the kind of actual tree-like structure of these graphs. So on the right here, what I've drawn is, actually, I think in the 2D case, this picture doesn't correspond to this one. I was a bit lazy to find the right picture, but this one does correspond to this one. So let's look at this one. So I think I've drawn from the bottom right-hand corner here, I've put that over here. And I've just then plotted the kind of the genealogical structure. So as you go from left to right there, the sort of distance away from this root vertex is shown. And so, yeah, maybe because it's kind of just quite cute, there's kind of some animations that show this kind of connection very nicely. So they were developed by this computer. Well, I guess he's interested in kind of visual representations of various kind of mathematical objects. And so this is kind of just showing how we can extract from the 2D or kind of a uniform spanning tree in a box here, we can kind of extract this tree. And this kind of gives you this kind of nice view that, you know, you could have had 2 points that were very close in the structure here, so in Euclidean space, but it kind of, you see these points here are still unpitched. So although they were close to something down here in Euclidean distance, they're very far away in the tree metric. And so we see this here. And like I say, just because it's maybe a bit more exciting than just listening to me talk, here's another one in in 3D. Hopefully it's showing a little bit clearly on the Zoom video. But yeah, so this is anyway, just mainly for the prettiness. So yeah, so I'm interested in the scaling limits of these things. So as you can see, we're seeing some kind of fractal type structure for these trees. And so yeah, what I've been interested in is proving actual scaling limits for these to continuous metric spaces, and in such a way that we can also understand, well, we don't lose this information about this spatial embedding. So when we kind of untangle this, reverse that map that I just showed, we kind of course, can put these trees back into space. And so I want to kind of also, when I take scaling limits, remember this spatial structure. And actually the other part of the story is that I'm going to want to also remember, say, the uniform measure, how that behaves if I kind of transfer, say, the counting measure on the vertices over here onto this fractal tree here, how that scales in the limit. And part of the motivation for this is that this is going to actually be all the kind of information that we need to actually understand also the scaling limit of the random walks on these graphs over here. And so although it might seem a bit like tedious in some sense, at least in the 2D case, the scaling limit of the uniform spanning tree was also already started to be explored by Oded Schramm. It might seem a bit tedious why we work sort of so hard to kind of refine the topology to include all this extra information. But like I say, one of the main motivations is understanding sort of the random walk on this, and sort of the intrinsic distance structure on this tree. And so that's kind of a big motivation for the work. And so that's kind of the starting point of the talk. Yeah, so scaling limits, how do we understand these? So like I say, well, there's a strong connection between the uniform spanning tree and loop arrays random walks. So in particular, if we take two vertices in the uniform spanning tree, it's known that this is a loop arrays random walk. So like say this goes back to P mantle. So if you don't know what a loop arrays random walk, this was a process introduced by Greg Lawler. So basically what we do is we run a random walk. Every time it makes a loop, we delete it and we carry on and so on. And well, this is a recurrent graph. So eventually it's going to hit any other point. And so if we run this loop arrays random walk from one point to the other, we eventually sort of generate a simple path between them. And this exactly describes the distribution of the path in the uniform spanning tree. And so that's kind of a very strong connection between these two models. Yeah, and maybe here's just, again, just to show a slightly larger scale picture. So this time it's taken from a book by Lyons and Perez. And so you can see here, this shows in blue here the unique path in the uniform spanning tree on this box between the corners here to here. So you see this kind of the kind of fractal structure of this path. And yeah, the heights of the other vertices, if you're interested, these are the distances from this path. So somehow to get up to this corner over here, we have to kind of climb the mountain kind of step by step, somehow around there maybe. And you can see these kind of big cliffs represent exactly the jumps from one cluster or one part of the tree to another part of the tree. And they kind of somehow represent how much intrinsic distance you're going to have to go between these. Yeah, that's one path in uniform spanning tree. And again, I suppose many probabilists at least have heard of how we can extend this to generate the whole of the tree. And so this was an algorithm introduced by David Wilson. And so, yeah, I'll be a little bit brief with this, but hopefully it's reasonably clear. So we start off by just listing all the vertices of Z2. So let's just fix x0 to be the origin, it doesn't really matter. And we start off by just taking that to be our kind of seed. We then run our random walk. So we know the path from the next vertex in the sequence, x1 to x0, is just a loop arrays random walk. So we just do that. So we run some random walk, we delete the loops to get a simple path, and we kind of make that our u1, our curly u1 here. And then we repeat. So from x2, we run another loop arrays random walk until we hit what we've already got. And we add that to the tree and so on. And so this gives us a sequence UK that's kind of an increasing sequence of graphs. And when we've exhausted the sequence of vertices, we end up with the uniform spanning tree. And so this is the algorithm, I should say, on Z2. And this gives us the uniform spanning tree on any recurrent graph. I should say, of course, those that kind of like details, you'll notice that Z3 isn't a recurrent graph. And so we can't quite start the algorithm like this, because if we run a random walk from x1, it might drift off to infinity before we get to x0. So actually the first step of the algorithm is not to take x0, it's to take a random walk from x0 to infinity, erase the loops, and then we run from x1 a random walk until we hit that path, and it will hit that path. And so this is the kind of recipe in 3 dimensions. Yeah, and again, like there's kind of nice videos of this available, so I have links on my website. So the original one was by Mike Bostock. So here's the kind of animation. So the white part is the part we already constructed. The pink here is the kind of loop erased random walk. You can see every time it hits itself, it erases. And at some point it hits itself, and we add that to the structure. And you can see, like at the beginning, it was a little bit slow, but as we kind of go on, so maybe I start it again. So it's a little bit slow at the beginning to sort of connect up to what we've already constructed, but as we go on, it gets kind of quicker and quicker. Yeah, and I should say that I'm just kind of going through, when I pick the new vertices, I'm just kind of going along sequentially along the lattice like this. But yeah, so this gives a nice construction. And actually part of the motivation for David Wilson to introduce his algorithm was to give a polynomial type construction of the uniform spanning tree. So of course, kind of generating all spanning trees and choosing one is kind of not a very sensible way to do this, and Wilson's algorithm gives you this much more efficient way. And so also on my website is this 3D one. I should say I don't know that I want to watch this, because I wasn't so careful as to put a seed that works quickly, and it can take a long time to start the algorithm. But if you kind of would like to watch this through, then you can find the link on my website. But like I say, it can take sometimes a little bit of time. So maybe it's not a good idea to give 5 minutes in a seminar to watching this now. So yeah, anyway, so this is the connection. And yeah, the nice thing for us is we're interested in scaling limit of the uniform spanning tree. What's well understood is scaling limit of the loop arrays random walk. At least in all dimensions apart from 3, I should say. And so this is just kind of a brief introduction to what's known about loop arrays random walk on the integer lattice. And so I apologize that the statements are a little bit vague here, but hopefully the ideas are reasonably clear. So the point is that in high dimensions, so dimension bigger than 5, the random walk we know is transient, it drifts off to infinity, and actually the sort of intersections of the loop, the self-intersections of the random walk are quite small. And so in particular, they're not enough to change the global behavior of the process. So actually in these dimensions, the loop arrays random walk looks pretty much like a usual random walk, and in particular, it rescales in the usual way to Brownian motion. So when I say rescales diffusively, I mean to exit a box of size n, it's going to take about n squared steps. The same is also true in 4 dimensions, just with kind of some logarithmic corrections to those scaling factors. And so these were results of Greg Lawler, who introduced the process, as I mentioned. The situation becomes a little bit more interesting in the lower dimensions, or I should say much more interesting, I guess, in the lower dimensions. And here, the self-intersections of the random walk really do start to matter. And so what's meant to be shown in this picture is kind of a 2-dimensional random walk run from, say, one point to another point over here. And so it's a little bit unclear, but the black path that you can see is the loop arrays random walk, and the gray part is all of the range of the random walk that was seen up to that time. So it's kind of all the vertices that were deleted. And you can see that we've deleted quite large sections of the path here. And so the behavior of the path is generally quite different to the random walk here. And whoops. So in particular, what's known is that it doesn't have this diffusive type scaling anymore. It has now an SLE type scaling. And so like I mentioned before, the kind of intuition for this was provided by Schramm, and Lawler, Schramm, and Werner kind of made this kind of convergence rigorous. And I should say that the sense in which they proved this is in the sense of compact sets. So namely, let's suppose you take 2 points kind of distance n away, you rescale things down so that they have distance 1 away. Then if you look at sort of the shape of the curve, then this converges in the sense of Hausdorff distance between compact sets to a random compact set, which is just the SLE, the shape of an SLE2 curve. So if you don't know what that is, it doesn't really matter. For this talk, you can just think of this as the scaling limit of this random path. So the thing that was missing in the scaling limit was exactly the sort of time scaling. So how much time, how many steps are left in this loop array's random walk. And so it turns out that the number of steps, if the kind of distance between these two endpoints here is sort of scale n, then the kind of number of steps of this path are going to be n to the 5/4. And so this is what this growth exponent is representing. And so this exponent was identified in work of Rick Kenyon, but the strongest results in this area has been proved by Lawler and Vikland. So in particular, what they show is that if you look at the loop array's random walk as a process from, say, a point, well, a set to a set, say, then this rescales as a process. So if you kind of rescale the space and speed up the time by n to the 5/4, then you can really understand this as a parameterized path, and it converges to some suitable parameterization of the SLE curve here. And so this is the sense in which we have a scaling limit. So the usual kind of uniform convergence of continuous functions here. So yeah, so we understand this well. So the hardest dimension, it turns out, for this model is the 3-dimensional case. And so here, not very much is really known. And so the big omission, I would say, from this whole story is the fact that we don't have any candidate at all for what the scaling limit in this dimension should be. So we don't have any kind of intuition for or what should be the natural kind of replacement for the SLE in this dimension. In some sense, it should be kind of Brownian motion, kind of growing away from its tip towards harmonic measure at infinity in some vague sense. But to make this rigorous is kind of a big, I would say, open problem in the area, and of course would be a very nice one for someone young and ambitious to be thinking about, I guess. But what is known is that we can rescale the discrete paths in the sense that we described down here. So the first result in this area goes back to Cosma, maybe I think now 15 years ago or so. So he showed exactly in the sense of compact sets, so just the shape of the path. Then if we kind of start a loop array's random walk from the origin and run it to the box of size n, then we can understand the scaling limit of this curve. And in kind of recent work, just from the last, say, 3 years or so, Shinyi Li and Daisuke Shiraishi have shown that if we include the time parameterization as well, then we can also show convergence. So namely, we can view this really as a random function converging. And in this case, the time scaling should be like n to the beta, where beta is known to exist. It's a deterministic constant, but the exact value is also still unknown. So this is just a numerical simulation by David Wilson. It should be somewhere around 1.62, but yeah, we don't have any kind of belief that it will be a nice number, certainly nothing like 5/4 is expected. And we don't even have any kind of equation that's kind of at all tractable as to how to solve this. We can only represent it in terms of other equally intractable quantities. So yeah, that's another nice problem, maybe to give a nicer description of this than ask the limit of the length of rescaled loop array's random walks, I guess. But yeah, I have nothing that I can add about that. So yeah, so that's what was known about loop array's random walk scaling. So yeah, let's go back to our model of the uniform spanning tree. And like I say, just to put our results into context a bit, I kind of wanted to underline that exactly in these kind of seminal works of Schramm, and in particular his first work on the kind of topic of SLE, he actually also in addition to describing the loop array's random walk scaling, he also described various properties that should hold for the scaling limit of a uniform spanning tree. And so here's the sort of sense in which he did this. So how he chose to view the uniform spanning tree was in this sense here, so the so-called ensemble of paths. So it's kind of, yeah, maybe not totally easy to get your head around, but basically he just views it as a whole collection of triples. So we just take any pairs of points in Z2 and the path between them. So we get kind of 2 points in R squared and some compact set in R squared, which is just representing this closed arc between them. And yeah, I put the dot on here because he compactified his space, just to avoid problems of what's happening at infinity. And so anyway, by making this compactification, this is actually also becomes a compact subset of this space. And so we can kind of study its limits in the sense of, again, Hausdorff distance in this space. And again, he didn't actually show in the original paper that the limits existed, but what he did show was that various topological properties that have to hold for any subsequential limit. And so a few of these are listed here. I don't know that I want to really discuss these, but essentially these kind of just gave started to give us an understanding about the topology of the scaling limit. And of course, from the sort of development of the SLE theory, we can also start to understand that, of course, each of the paths that appear in this limiting tree have to be an SLE2. And so somehow if we choose a finite number of points in space, then we're going to get kind of somehow a web of SLE2s. So maybe if we take this point and this point, we get one SLE2. If we add a third point, we get some SLE2 that runs until it hits what we've already constructed, and so on. So we get this kind of Wilson's algorithm in the continuum. And actually as well, in his paper, he also gave an argument that if we want to describe the piano curve that goes around the edge of the uniform spanning tree, so we just kind of draw the continuous curve that maps around the edge of this tree, then this has an SLE8 scaling limit. So it's also described within this SLE8 framework. And so this was kind of Schramm's contribution in this direction, which of course is very substantial. But I should say the thing that was missing in this picture was that this contains, of course, no information about this intrinsic distances of the graphs, or the kind of volume of the graphs in terms of the sort of counting measure and how that rescales. Of course, when we kind of embed the counting measure into R squared, of course, the counting measure is just uniform, right? So it's kind of, we can understand that, but in terms of us, the kind of tree-like structure, how it kind of fits with the tree-like structure, it's kind of not really contained in this picture. Okay. Yeah, and actually, I guess as well, this kind of explains, this last comment also explains why we take this slightly complicated topology here to understand the scaling limit, because of course, if we just view this space as a compact set, then of course, in terms of Hausdorff limits, it's just going to fill up all of R squared, right? So it's not a very interesting topology to think about these things in. Okay, but so the goal of our work was to kind of add this extra information. And this really goes back to work that Martin Barlow did with one of his PhD students about 10 years ago, where he started to kind of get a feel for this. And in some sense, this work kind of showed you that the things that you would guess to be true are true. So like I say, let's suppose we're looking at a Euclidean ball of size r. So let's think that's the sort of scale of this picture here. If we're kind of talking about the length of a loop array's random walk here, we expect this to have length r to the 5/4. And so it's not totally surprising that if we draw this uniform spanning tree ball, so I think this is what's meant to be shown in red here. Maybe I didn't count the steps, but if you get bored in the next 2 minutes, you can work out the radius of this ball in the uniform spanning tree. But the point is that shouldn't be that surprising that this ball should look something like a Euclidean ball, or you might hope it does. And this is exactly what they showed with high probability, that at least up to sort of constants, this is true. So namely, we can include kind of, with high probability if lambda is big enough, a kind of a rescaled version of the Euclidean ball inside the uniform spanning tree, and one around the edge here. like this. And so that was a result of Barlow and Masson. And just a bit more specifically, like it's easy from this to kind of see how the exponents map to the volume of balls in the uniform spanning tree. So in particular, so if I just shift this exponent over here, then I see that the ball of radius r here has radius r to the 4/5 in Euclidean sense. And we know, of course, in Z2, then balls have of sort of size r have, of course, r squared points. And so this point here, this ball in the uniform spanning tree should therefore have about r to the 8/5 points. And so this is what this result shows. So like I said, it's kind of what you would guess, but we're kind of checking this in a very precise way. So yeah, this is where we were kind of starting from, and our question is, can we kind of refine the topology of Schramm using this kind of information? This is really our goal. And so here's the framework in which we chose to work to encode all of the information we wanted. And so yeah, before I talk about the topology we care about, I'll just talk about the objects that we use to encode the uniform spanning tree. And so this is going to be a quintuplet of things. So I'm going to call measured rooted spatial trees. And so the basic objects here are first of all the metric part. So T here is just going to be the vertices of the uniform spanning tree. So this is just going to be Z2 in the 2D case. And this DT is just going to be the intrinsic metric on that space. So just the usual graph distance on that space. Yeah, actually, the way I wrote it here, I'm assuming that these are real trees, and so these are kind of metric space versions of graph trees. Yeah, again, people that kind of attentive to detail will notice actually in the definition of real tree, you really need the trees to be connected. So I suppose I should really include the line segments on my discrete model, but of course this is kind of a small detail. So these are anyway this first pair here. The third thing I'm going to throw in here is going to be just a measure, and in particular, this will be my counting measure on the uniform spanning tree. And so the next thing that was kind of, like I say, missing from the intrinsic sort of distance part of the tree is the kind of spatial information. And so this is what this phi is representing. And so we represent this information using a continuous map. So essentially, this is just the identity map on Z2. But really what we're thinking of is this is a map from the vertices of the uniform spanning tree with their intrinsic metric into Euclidean space. And so really this is the change of metric from the tree metric to the spatial metric. And finally, because we've got infinite spaces, it's kind of useful to fix a sort of center to them. And so we're going to it's going to be convenient to have a root vertex. So this will just be the origin, for example, of Z2 or whatever other favorite vertex you have, I guess. And so these are going to be the things that we consider. And yeah, given how much time I have left, I don't know quite how much I want to talk about the topology of these spaces. But in particular, we're going to use something called well, it's not really called this, but we're going to use a generalized Gromov-Hausdorff type topology. And so for people that haven't met Gromov-Hausdorff type topologies before, this is just a natural notion in some sense that captures a convergence of metric spaces. So maybe if you've seen any of kind of Christina's talks on kind of scaling critical random graphs or trees or minimal spanning trees and so on, then you might have met this before. The reason why we're sort of generalizing it is that the kind of traditional Gromov-Hausdorff, the original Gromov-Hausdorff topology just deals with metric spaces, compact metric spaces. And so not only do we need to consider locally compact ones, which anyway, there's plenty of discussion of this in the literature, we also want to introduce the measure and also this kind of these maps phi as well into the story. So yeah, maybe just for 2 minutes, I think this isn't going to be very helpful for people that haven't met Gromov-Hausdorff topology before, but and probably the people that already have met them before, this is kind of, you know this already, so I'm not quite sure who this slide is going to help, but let's quickly see. So a bit more precisely, here's how we define the distance, the kind of classical Gromov-Hausdorff distance between compact trees. So what we want to do is kind of, let's suppose we've got a tree over here and a tree over here. We want to embed them into a common metric space isometrically. by some embeddings, say psi and psi dash. And we just measure the distance down here with respect to the usual Hausdorff distance between compact sets down here. And we do this in a way that's kind of optimal. And in this picture here, you can see if I kind of thinking of the intrinsic metric here along the line segments, then I can kind of map this tree onto this one. And so actually these two are kind of equal with respect to this Gromov-Hausdorff type distance. Another way to think about this is in terms of correspondences. So a correspondence is just kind of a matching between spaces. So every point in the left one has a kind of corresponding point in the right, and vice versa. These don't have to be one-to-one matchings. They're just kind of subsets of the product space. And again, we look at kind of how the distances in the one space match up with the corresponding distances in the other space, where these kind of x and x dash and y dash are corresponding points. And we look for the kind of worst case of this over the space, and we kind of optimize over correspondences. And this turns out to be an equivalent definition. And the reason I kind of included this slide was really for this slide here. And this is kind of maybe, again, for experts, really, just to kind of describe the topology. So to introduce the measure and the embedding, we start with our original Gromov-Hausdorff topology, which is this part here. But we also include the measures. So when we do this embedding, we don't just want the spaces to match up, we want the measures to match up down here. So that's this middle term. And then this final term here deals with the embedding. So basically points that are kind of close in this embedding down here should also have similar spatial position over here and over here. And you can see that if I kind of am thinking about the spatial position of this, then this doesn't kind of match up with this. And so although the metric structure is the same, the spatial structure kind of isn't. And so these trees maybe aren't going to be equal in this kind of generalized version of the topology. And so it's kind of a finer topology than the original one. And so this is the topology we're interested in. And so here's the main result, really, of the talk. So yeah, it's coming a little bit late in the day, but the point is we can prove convergence in this topology. So that's all you really need to understand from the talk. Then if you understood those words, then that's kind of, yeah, everything else is kind of just details. So again, just to underline, here's the uniform spanning tree. We rescale the graph. So the underlying Z2 just have kind of lattice spacing delta. Loop array's random walk spacing is delta to the 5/4. So we rescale the intrinsic metric by this. The counting measure needs to be rescaled by delta squared. So this is, of course, just matching up with this delta over here. Then we can show that these things converge in this topology. And so the basic point is we start off, so these points here aren't meant to be the whole of Z2. These points are meant to be just some finite set. So we first of all exactly establish that the tree spanning this finite number of points converges. And so, like I say, this is kind of essentially contained in the work of Lawler and Wickland. So they prove it for a single path. But the nice thing about SLE is because of this whole conformal invariant story, actually these kind of statements are very robust to changing the domain. So actually the subsequent paths are also kind of contained in their theory. And so the subsequent paths are still kind of, we understand that these converge to some SLE type curve. And so, yeah, why I kind of broke this down into tightness and convergence is because in the original paper that we wrote, at this time, Lawler and Wickland hadn't proved convergence. And so we had to ourselves work to prove the tightness of these kind of things. And actually in this later work by Nina Holden and Jin Sun, they kind of had access to this work of Lawler and Wickland. And so they were able to then combine our kind of tightness result with the scaling of single paths to get the full convergence. And so that's why I put both of these papers up here. And so that's the kind of the finite dimensional marginals in some sense. And then we need to then add the rest of the points in Euclidean space. So these are these red points here. So what we want to do is just show that eventually, as long as we chose enough black points to start with, then everything else is somehow close. So we don't have too many points like this, or there's not too much influence from points that sort of travel a long distance and before it connects up to what we've already got. And this is where we use these kind of uniform estimates of Barlow and Masson to sort of understand whole sort of regions of space simultaneously. And so this is actually where a lot of the technical work was going in this paper. Okay, so that's the 2D story. So yeah, I've got a few minutes left, which is good. So the nice thing I should say, like I say, about including all of this detail about the metric and the measures up here is that this kind of some kind of very natural properties transfer from the discrete to the continuous case using this kind of topology. And so in particular, things like volume estimates. So namely, we have a limiting space to begin with. This is the first observation. So this is just a random metric space tree. So equipped with an embedding into R squared. It's got a measure on it. And we can check these kind of estimates of Barlow and Masson, they transfer into the limiting space in a kind of natural way. So we have these kind of volume estimates, and these of course immediately tell us that the Hausdorff dimension is 8/5, as you might kind of have guessed. And also I should say that we can recover as well from these kind of topology, many of the topological properties that Schramm noticed. And so maybe I should say, yeah, this property here looks again a little bit heavy to read, but the point is if I take off all the leaves of this tree, so all the degree 1 vertices, so somehow all the points at which if I remove them, this metric space stays connected. So this is this TOO here. Then actually this is homeomorphic to its image in Euclidean space. And so what this means is actually, if I kind of go back to this picture of Schramm's over here, it's kind of clear that somehow in the limit, if I take kind of points close to this one and this one here, then I can get points kind of arbitrarily close in the limit, but which the path kind of has to still go round all the way around here. And so in particular, I'm going to have 2 points of the tree that might be a long way away in the tree, but sort of map to the same point in Euclidean space. So this map in the limit, this map phi is not an injective map here, but actually the only intersections happen at the leaves. That's what this statement here says. And so the other thing that kind of is a natural property asked about is things like the branch points of the tree. So we can show that this is a maximum branch point of 3, and this is actually also equal to the maximum number of pre-images under this embedding. And so the fact that these are equality is not as a coincidence. This is to do with the duality, the self-duality of the uniform spanning tree. So the dual graph of the uniform spanning tree, if you know what that means, has the same law as the uniform spanning tree itself. And so that's a very useful property in 2D. So finally, yeah, I don't think I'm going to have time to talk about random walks in any great detail today, but I should finally say that, yeah, I want to kind of describe what the differences are in the 3D case. So we can prove the same result essentially in 3D with the appropriate change of exponents up here, at least along a subsequence delta n is 2 to the minus n here. So the reason for this subsequence is purely due to kind of Cosma's result, actually. So in his original paper where he showed that the sort of shape of the paths converged, then he proved things along this subsequence. I think there's no particular reason to believe this is needed, and actually our result shows tightness along an arbitrary sequence. So in fact, it's not an essential condition to have a geometric series like this. So that's the first kind of comment, and I just kind of, I guess, mainly wanted to highlight what the kind of extra work that was needed here. And that's kind of essentially corresponds to the 2 points that I mentioned in the 2D case. In each of these cases, there's kind of an extra difficulty in the 3D case. So when I do this first step, when I kind of look at the finite part of the picture here, actually, although Schiller, Ishii, and Lee showed that kind of loop arrays random walk converges, they proved this in a regular domain. And unfortunately, like, because we don't understand well the scaling limit, we don't have, it is kind of not an immediate kind of consequence of their result that we can read off that therefore the same is true in irregular domains. And a lot of the problems come from the fact that in 3 dimensions, unlike in 2 dimensions, simple random walk doesn't hit paths arbitrarily quickly. So just to kind of clarify a little bit, so if you start a random walk in 2D next to a line, it's going to hit that line very quickly. So before it kind of escapes some global distance, it's going to hit the path. This isn't true in 3 dimensions. If you start kind of a random walk next to a straight line in 3 dimensions, it can go to infinity before it ever hits. And so this is a bit of a problem for us because it means this second part of the algorithm where I kind of add on the rest of the tree, I have to be a bit more careful. But fortunately, this was solved in a sense already before we came to our work by already Shiraeshi and Sapochnikov. So in another kind of context, they actually showed that although it doesn't hit straight lines quickly, simple random walk does hit loop arrays random walk quickly. It's just got a big enough dimension kind of that we do hit this this quickly. And so in a sense that the proof is pretty similar, but this is kind of an extra technical headache, and in the sense that it means we have to remember much more what parts of the tree we've already seen when we kind of look into the future part of the construction. And so, as you can imagine, it's kind of, yeah, a little bit more nasty to write down all of these events, which was a big part of the problem. Yeah, again, we can write down sort of similar properties for the limiting space, or at least some of them. So things like measure estimates, we can write down the same in terms of which gives us a Hausdorff dimension in terms of this growth exponent at least. I should say the topological properties, though, the fact we don't have this self-duality in 3 dimensions means that we can't use some of the soft arguments that we used in 2D. So things like the maximum degree being 3, we don't know. We conjectured this is true as well. Maybe also, I mean, that's kind of nice, but kind of it's almost more interesting the differences between the dimensions. And so actually we suspect, so the trunk, so the part of the tree that's not the leaves, in this case it's not a tree. So namely that the sort of intersections in 3 dimensions don't only happen at the leaves in 3 dimensions. So somehow the trunk itself can intersect with other vertices. And so this is yeah, quite a different sort of topologically in this case. Yeah, just to finish with, in the last 2 minutes, maybe I want to say a very brief word about the simple random walk. So, because like I say, this was kind of the motivation for this story. So, I mean, we have a graph, connected graph, we can easily run discrete time simple random walk on this space. So this picture here just shows the range after 5,000 steps on the left. So I think the red vertices are the vertices visited the most, the blue ones the least. And this is the same picture after 50,000 steps on the right. And well, we kind of, I guess, again, if you've kind of studied random walks on sort of graphs before, you probably have met the connections between these and the effective resistance on graphs, electrical potential theory. So there's many kind of ways in which we can see this connection. The nice thing is actually, of course, on a tree, the resistance metric is just the actual intrinsic metric. Somehow, you know, if you ask what's the resistance between 2 points, if I put unit resistance on each edge, it's just the series law tells us this is just the graph distance. There's no parallel path to remove connections, you know, to change the resistance. And so this kind of intrinsic graph distance of the tree contains all of the information about the random walk. And so the fact we understand the scaling limit of this and also its invariant measure means that after a bit of work, it's actually enough to also tell us about the random walk scaling limit. And so according to sort of general results that, well, you can see I kind of missed quite a lot of slides there. So if you want a very brief version, you can look at the missing slides, but there's kind of general results which say that if we understand the scaling of the metric and the measure on trees, then we can also understand the scaling of the random walks. And so this is just with the kind of natural parameterization that comes out of the other parts of the story, we can understand that the random walk up here converges to some limiting process that's kind of a natural diffusion on the limiting tree embedded into Euclidean space. And so that's the kind of limiting object that arises. Yeah, just to show one final kind of pretty slide is that actually this story turns out to be a bit more general. So here we go. So the story of kind of metrics and measures encapsulating properties of random walks, if I replace that graph distance with resistance metric, it turns out that this is a kind of useful way to view random walks on other kind of graphs. And so in particular, there's a general result that says that if the resistance metrics and the measures converge, then so do the random walks. And so this kind of theory was kind of pioneered in the world of self-similar fractals with the motivation of understanding random walks on critical percolation clusters. And so since its kind of introduction, maybe 30 years ago, it's kind of become more and more robust to the point where we can understand random walks on various families of random graphs. So like the uniform spanning tree, this is the continuum random tree, stable trees. This is a critical Erdős-Renyi graph. This is a loop tree, a stable loop tree, if you know what this is. Then we can understand the scaling limits of all of these kind of random walks using this same picture. And yeah, I think the theory has now become very close to the point where it's actually not so far away from understanding random walks on critical percolation, at least in high dimensions, which is kind of a very nice kind of, I guess, full circle, I guess, in terms of the development of the theory. Anyway, I probably have talked for a little bit too long, so I should probably stop. And yes, thank you for listening.
Thank you, David, for a beautiful talk. That was fabulous. Yeah, I would like to invite people to ask questions. So if you would like to type your, sorry, Alex tells me he has a question, but anybody else who would like to, please just type in the chat or raise your hand and we'll unmute you. Maybe I can start with one, which is just about universality. So everything you've done here was on the integer lattice, but presumably one would expect that this should be true for other 2- and 3-dimensional regular lattices.
Yeah, so I think in 2 dimensions, there's even a paper by Yedin and somebody else, sorry to forget the name, but that shows essentially, if you know simple random walk converges to Brownian motion, then the loop array's random walk will converge to SLE. And so, yeah, I mean, it doesn't take huge imagination to therefore believe that the same should be true then, therefore, for the uniform spanning tree as well. It should have the same scaling limit. Yeah, so I think in 2 dimensions that's kind of understood. Yeah, in 3 dimensions, of course, you would guess the same is true, but yeah, we have nothing concrete to say about the limits. So I guess with Daisuke's techniques, he could probably show that for any random, yeah, maybe he can show that a limit exists, but of course, the fact we don't know what our limit is already matching up it with other models is, of course, yeah, a bit beyond us at the moment, I would say. But, yeah, it's of course a natural question to try to do that.
Alex, go ahead.
Yeah, David, thank you for a lovely talk. So actually, Christina just asked one of my questions, but but my other question was, so in 2 dimensions, you said that the limiting tree has almost surely a unique end, a single end.
Yeah.
Right. So from the origin to infinity, or from anywhere to infinity, you get some path. Can you say anything about what that path looks like? Is it another? Does it look like a loop array's random walk, or is it something completely different?
Yeah, so I think, yeah, maybe in 3D it's maybe easier to even understand, because exactly in 3D we have the same property, and exactly if you think about the start of the construction here, you just have one single path that goes off to infinity, and so yeah, the path will be the scaling limit of that path, which I guess plays the role of the SLE in the 3-dimensional case. So in that case, yeah, I guess the best person to answer this is probably Daisuke, who kind of, yeah, I believe has results even that says that talks about, yeah, the random walk condition not to intersect for a long time. But yeah, I think it should be essentially like a version of the SLE kind of. I guess the point should be that it should be, if you take an SLE and you like to just a finite ball and you kind of zoom out, or zoom in, I should say, sort of rescale the part around the center, so just let the ball size go to infinity. It should be this limiting object here. So yeah, I think, yeah, probably, yeah, Daisuke can tell you exactly what the model is, even in 2D. I mean, even in the discrete case, I think he has a description of this conditioning, and I think it should be, I don't know if it's written down, but it should be essentially the scaling limit should be this kind of zoomed in version of the SLE, kind of SLE close to 0, I think. So yeah, I don't know if, like I say, if that's really written anywhere, but it should be described in that way.
Thank you.
Anybody else have a question? Now's your moment. Oh, one from Mikhail. Let me just, I'm just going to try and unmute you, Mikhail. You should be able to unmute now.
Yes, can you hear me?
Yes, we can.
Oh yeah, I can hear.
So you use the result from Holden and Soon in your to prove your main theorem. So they have this this convergence of both the UST and the dual UST in their paper. I mean, do you rely on that to prove your theorem? The fact that you have this joint convergence?
No. So actually, this paper came before Holden and Sun. So in this paper, we just showed tightness. So we showed, for example, Louperay's random walk paths are tight. So yeah, of course, the fact that they have this sort of dual convergence, though, I guess it means that it wouldn't be, again, very difficult to put here kind of a coupled version of the dual tree, and that would simultaneously converge, kind of combining. I mean, our statement would already tell you that these two things, both the original tree and the dual tree, are tight, and their result would give you, in this topology, sorry, and their result, their kind of additional information provided by their work would, of course, then give you the convergence, the simultaneous convergence in these spaces. So yeah, it should be possible to write that down, and so in theory, you'd get a dual version of the limiting tree, which should kind of exactly interleave with this version that we have here. So we didn't use it, but yeah, it should be true.
Okay, I understand. Thank you.
I can't see anybody else. So what I'm going to do is I'm going to stop recording and I'm going to propose that